everybody. Thank you for coming to our physics colloquium. And I'm very delighted to have Dr. Shaikh Saad today as our speaker. He's from University of Basel in Switzerland. Dr. Saad did his undergraduate study in Dhaka University in Bangladesh. Is that correct?
Yes.
And after that, he went to Oklahoma State University. So in the place where I also studied there. And he worked under the supervision of Dr. Kaladi Babu. And after that, he served as lecturer also at the Oklahoma State University before finally got a postdoc position at Basel University. He's very productive scientist, and his main specialty is grand unified theory. And today he will tell us about the introduction to grand unification. So Saad, please go ahead and give your presentation.
Okay, thank you. So thank you, Julio, for the introduction. Nice introduction. So as Julio already mentioned, my name is Saad, and I am a postdoc at the University of Basel. And today I'm going to talk about grand unification. It's a very introductory lecture, as already Julio pointed out. So the outline of the talk is something like this. First, I would like to briefly talk about this quantum world. And from there, I will actually show that standard model is a very good theory which describes our microscopic world. But then briefly, I will talk about what are the problems in the standard model, the problems of the standard model. And then I will talk about why grand unification is required or is motivated. What is the corresponding motivation for it? So let me just first start with the quantum world. So Julio, one question. So are people going to ask, I mean, people can ask questions anytime they want.
Okay, sure. So if you have any question, please do not hesitate to ask the question. Just interrupt the speaker anytime by raising your hand.
Right, that would be great. Okay, thanks. So let's first talk about our classical world. So in the classical world, let me take a very simple example, which is we know Earth is rotating about its own axis, and that takes about 24 hours. And this rotational motion is described by spin angular momentum. We also know that Earth is rotating around the sun, and it takes about 365 days for one complete rotation. And this rotation is described by orbital angular momentum. So if we want to describe the total rotational motion of our Earth, we just have to properly take a vector sum of this orbital angular momentum and the spin angular momentum. But the main important thing is, in our classical world, all the different components of the spin angular momentum and the orbital angular momentum can be measured exactly at the same time. This is first important point. And the second important point is all these different physical quantities are continuous variables. That means they can take any value they want. Now, let me quickly then go to the quantum world and compare it. What are the differences? Now, we know in our quantum world, atom has a center, which is the nucleus. And about this center, electrons, these electrons are rotating. This is just a rough idea about how electrons rotate about the nucleus. And just like our Earth, this electron also have a spin angular momentum. And since it is rotating about the center of the atom, it also have the orbital angular momentum. So everything looks very similar. However, there are two major differences. First one is all the different components of this orbital or spin angular momentum cannot be measured at the same time, because this is quantum world, which is experimentally proved. And also these components, they don't take any value you want. They are quantized, meaning they take only very specific values. So these two are the most important differences with respect to the classical world. And those are already very well known and experimentally verified. And rest of the talk will be based on this. Okay. So just to give an idea, we talked about electron, but let me generalize it a little bit. So since we cannot measure everything simultaneously, a convenient choice is we only measure the magnitude of the spin angular momentum, and we measure one of the components, and typically we choose it to be the Z component. It doesn't matter. You can choose whatever the component you want. But the main important point is, if you talk about the quantum world, then once you know the spin of the particle, you know exactly how many states are associated with that particle, which is exactly given by 2s plus 1. And this s is called the spin of the particle. As I described, it is not continuous, but it is quantized, meaning it only takes discrete values such as 0, 1, 2, or half, 3/2, 5/2, and so on. So the quantum world is described how actually they behave under some statistics, and that actually depends on whether the spin of the particle is half integer or integer. If the spin is integer of a particle, these are called bosons, and they obey a very certain behavior which is determined by the Bose statistics. Similarly, the half integer particles, these are called fermions, and they obey a very specific statistics which are known as the Fermi statistics. So this is the main difference, that how quantum world differentiate with respect to the classical world. And once the spin is known, we know exactly how it should behave. So let me proceed. So then the question is, okay, so we are trying to describe fundamental particles such as electron. So how does really electrons behave? To answer that question, the framework that we require is known as the quantum field theory. And quantum field theory is nothing but a combination of all the known theories that we know, such as electrodynamics, quantum mechanics, and special relativity. Once you combine all of those things, the new theory that we get is called the quantum field theory. And the purpose of the quantum field theory is to describe how the fundamental particles, excuse me, such as the electron, are interacting with each other. And this is precisely what we know, that electron must be a fundamental particle. It is moving around the atom, and we briefly know about how they interact, but a proper theory, which is the quantum field theory, tells us exactly how to explain it. Now, then the next question will be, so what is the theory of our universe? And it turns out that based on the quantum field theory, we came up with a very good theory, which is known as the standard model, that describes our universe. So that means it describes our nature. So then the next question is, what are the fundamental particles we have inside the standard model? And it appears that we have two different types of particles, of course, as we already discussed. Fermions, those are the spin half integer, and bosons, those are the integer spin. But experiment shows that in the standard model, fermions only take spin half. No other, let's say, there is no 3/2 particle, there is no 5/2 particles, and so on. We don't see those in our nature. A standard model describes our nature, and our nature experiments tell us we only have a spin half particle. And what about the bosons? Also experimentally, we have proved that in the standard model, we have two different types of bosons. One is spin 0, and another one is spin 1 particle. then you can ask the question, so what are the different types of fermions we have in the standard model? It turns out that we have two different. One is called the quark and one is called the leptons. How are they different? I'm going to get back to it soon. And about the boson, again, please remember that in the standard model, we have two different types of boson. Spin 0, which we call the Higgs bosons. Later it will be important. And then spin 1, those which we call the vector bosons or the gauge bosons. Then you can also ask the question, what do they do? Well, all the fermions that we see in the standard model or in our experiments, they actually make up all the matters. So all the particles that we have inside our body are basically made up of quarks and leptons. So our body, the entire universe that we see in general are made up of nothing but quarks and leptons. So what about the Higgs bosons? Well, Higgs bosons serve some important purposes, and I'm going to get back to it a little bit later. But let me talk about the gauge bosons. These gauge bosons are nothing but the force carrier. We know that in nature, there are different types of forces, but how these forces are carried among different particles are described by these gauge bosons. So these are the main difference between the particles and what they really do in, or what purposes do they serve in our nature. So any question up to this?
Is there any question? Please raise your hand if you need to ask question. Otherwise, Saad will continue his talk.
Okay, great. So this is the basic building block of the standard model. So then you can ask the question. So I have a very simple example. What do I mean by force carrier and how they actually help describing our interaction? And a very well-known example is, we know that if we have an excited atom, to get back to the normal state, it radiates away the energy. How does it do it? It just radiates away the light. So from an excited atom, whenever it goes back to the normal state, it basically radiates the light, which we call the photon. And this photon is nothing but a force carrier in the quantum field theory. And the same thing, whenever we talk about two electrons interacting with each other, let's say two electrons are coming near to each other and they bounce off. They are coming together and they exchange momentum and they go away from each other. How this bouncing is happening, or let's say we call it a scattering, is nothing but mediated by the force carrier, which is exactly the same as the light. We call it the photon. So this is a fermion. This is another fermion, electron. They are interacting via force carrier, which is the photon, in this case, the gamma. But let me talk a little bit more about the electron. Okay, so as I discussed, electron is a fermion. It has a spin half. And if you actually remember the thing that I mentioned a few minutes ago, how many states this electron must have is entirely determined by this spin. And for the electron, since the spin is half, it can have two different states. So what are the states? Spin up and spin down. That's it. So since it has a spin half, it is associated with the spin up. You can imagine like this way. If the electron is rotating about in its own axis in the anti-clockwise direction, this state we call the spin up state. If the rotation in the clockwise direction, we call it the spin down state. So electron is a kind of a fermion that consists of two different components, and together it forms an object which we call a spinor. And this is exactly what we are going to talk about a little bit more details. But to go about a little bit more details, I need to briefly give you an idea about what groups are. And let me start with a very simple example, which everyone knows. from the classical mechanics. So whenever we learn our classical mechanics, we talk about rotations in three-dimensional space. So we know that to describe any rotation in three-dimensional space, it must be specified with three different angles. Phi, which is a rotation with respect to the x-axis, and then theta, which is a rotation about the z-axis. And furthermore, there is a psi angle, which is basically determines a rotation of this xy plane with respect to this line. Once we know exactly how these three angles are changing the rotation of any object, we can describe any rotation in this entire three-dimensional space. But the more important thing that I want to mention is, if you start with a vector in a three-dimensional space, make any arbitrary rotation in a three-dimensional space, no matter what you do, the magnitude of the vector can never be changed. That's the most important thing about rotation. So any such rotation is described by an element which we call the which we denote by 3×3 orthogonal rotation. We start with a vector since it's a rotation in three dimensions. So this vector consists of three different components: x component, y component, z component. A general rotation of this angle is contained in this 3×3 orthogonal rotation. Once we make a rotation, we get a new vector. We denote it by x prime, y prime, and z prime. But as I described, no matter what arbitrary rotation you make, you can never change the magnitude of this vector. Everything that I just described is very nicely fit into a group which is called the SO3 group. 3 because it's three dimension, O because these rotations are described by the orthogonal matrix. So O represents the orthogonal. Okay, so this is the basic thing which we all know. Why am I describing this? Because a few minutes ago, I talked about the electron, which is a spinor, and you can think of how to describe the dynamics of this spinor, which is exactly nothing but a group, and which I'm going to talk about, which is basically called the SU2 group. So you can think of a spinor, which is an object on which the elements of the SU2 group, which is denoted by 2×2 matrices, will work on, and you get a new spinor. But no matter what, just like this, since you cannot change the magnitude of a vector, so when the objects of the SU2 is acting on the spinor, you can never change the spin. If it is an electron, it always has a spin half. You get back another spinor, but it is again has exactly the same spin as half. And this entire thing is determined by algebra, which we call the SU2. So any object on which these group elements are acting on is called a representation. Just like the electron, which is a two-component object, and that's why we call it a doublet. So electron is a doublet representation, and so on. So the main point is the vector of SO3, you can consider it nothing but a object on which the group elements are acting on. So this vector is a representation. Everyone knows about vector, but the mathematical term is a representation. So just like electron, it's a doublet representation. So why I talked about it, let me try to relate it with something that we already know. Okay, so we know that the center of the atom has a nucleus, and this nucleus basically consists of neutrons and protons. And experimentally, we have measured their masses, and it appears that their masses are very, very close. if you take the difference between the mass of the neutron and a proton, you see that the fraction is extremely small, which kind of gives us the idea that neutron and proton are basically the same thing. It's just different states of the same object. We can call it the nucleon. So what Heisenberg proposed is, we just like the electron, we have one object, which is the nucleon, but just like spin up and spin down of the electron, we have two different states. One is the proton state. You can call it a spin up state. And the other state is again a nucleon, but it's the spin down state. So combinedly, a proton and neutron form a doublet representation. They are the same thing, having exactly the same spin, but a state of the two different states corresponding to two different spin. But let me clarify, this is not exactly the spin because it's the entirely different space. And this is why we call it the isospin space. This is not really the spin state, but the concept is exactly the same as the electron. That's the point. And the nucleon system can be completely described by exactly the same SU2 group. So that's the point I wanted to make. So then the question is, okay, so we understand that nucleon is a fermion having a spin half and two spin up and spin down. So the obvious question is, what is then the nuclear force carrier? We already explained what are the nucleons, what we have inside the nucleus. But how do they interact? So the question is again going back to the same thing. Since proton and neutrons are fermions, spin half object, their interaction must be described by the boson. That means spin 1 state or isospin 1. And you can do a little bit of group theory and you can show that 2 by 2, which is doublet and doublet, will give you a triplet. But the point is, this triplet is nothing but something that has spin 1. That means it's a gauge boson or it is a force carrier, which we already talked about in the introduction. Now, being a spin 1 state, it must have 3 different states associated with it. That's why it's a triplet representation. And these 3 different states must have 3 different charges. Charge 0 state, which we call the neutral pion, and then a positively charged and the negatively charged pion. So they are the force carriers. Sorry, is there a question? No. Okay. So the point that I want to mention is, just like the electron, the proton and the neutron interact via the force carrier, which we call the pion. And here you see that just like the electron, we can describe the scattering. A neutron is coming, it is emitting a neutral pion, and then that neutral pion is interacting with an incoming proton. And this is how proton and neutron interact with each other. But on the other hand, whenever a neutron is coming and it is absorbing a positively charged pion, so it basically absorbs the pion, but neutrons are basically 0 charge particle. So whenever it absorbs this pion, it becomes positively charged. So it converted into a proton. And similarly, when this proton is coming and it is giving away a positively charged object, it becomes 0 charge object. That means a proton is converting into a neutron. So it is amazing to realize that this thing, before we discovered it in the experiment, Yukawa already proposed it just by using the concept of SU2 group theory. And later it has been proven in the experiments, which really tells us that our universe definitely knows about group theory. Every fundamental particle that we have and have discovered all of them precisely obey the rules of the group theory. And this is why Yukawa got a Nobel Prize a long, long time ago. So any question up to this?
Question, please raise your hand if any. Go ahead.
Or you can just speak up.
Yeah.
Okay, so
maybe
since
later.
Okay, maybe later.
There's
okay.
a question. There is a question.
Okay.
Go ahead, Patipan.
Hey, can I ask a question here?
Yes, please.
So you were saying that we using group theory to determine that it's a triplet, right, of isospin triplets, right?
Yes.
The force carrier, but why it has to be a scalar particle? I mean, it could as well be a vector particle, right? So is there any kind of similar argument that said it should be a scalar? Yeah.
Okay, so this is actually an excellent question. Okay, thanks for the question. So let me quickly go back. So as I was mentioning, so actually all the particles are classified into fermions and bosons. And we have seen that fermions are spin half particles and bosons can be spin 0, 1, and 2 and so on. So your question is a little bit technical. I am not going to go too much details into it, but the answer is yes. If we want to talk about the gauge boson, which are basically the force carrier, they can be, at least in our standard model, they can be of spin 1. You cannot have a force carrier, which is a fermion. And the main reason is actually their corresponding statistics. They follow some quantum statistics, which are known as the Fermi statistics and Bose statistics. A fermion can never be a force carrier. And if you do some complicated field theory, you will also realize that spin 0 can never be a force carrier. So the only way you can describe the interaction between a neutron and a proton can be a spin 1 particle. So as I said, it's an excellent question, but it's more involved. It depends on the representation of the Lorentz group. And I don't want to go too much into technical thing. Does that roughly answer your question?
Good. Kind of, but you can go ahead and think about it.
Okay, yeah. So actually, we can maybe talk about it later. It's actually more about, okay, since we talk about the field theory, so quantum field theory are actually defined in some space, which actually obey Lorentz transformation, and which can be a fermion, which can be a gauge boson. Those all determined by what are the corresponding representation under the Lorentz group. And that actually determines that this gauge boson or the force carrier can only be vector representation of the Lorentz group. So it's more technical. Okay, so we can maybe talk about it later. Okay, thank you.
And there are 2 more questions.
Okay, go ahead, please.
Yeah, Firdaus, go ahead. Firdaus Nusur.
Okay, thank you, Mr. Julio. I will ask, why are protons and neutrons called the same particle? Are proton composed of up down and neutron made up of down up? Why are proton and neutron called the same particle? Thank you.
Okay, so again, an excellent question. Yeah, so this is an excellent question. I have not talked more details into it. So you are right. Proton and neutron are not the same particle. You are exactly correct. Because we already know proton has 1 unit of positive charge. Neutron has no charge. It's a neutral particle. So they cannot be the same particle. However, what here I'm talking about is an approximate theory where you can at first completely forget about any interaction which is related with the charge. And then talk about, let's say I only want to focus on what is going on nucleus. And we already know that inside the nucleus, we have a kind of force which is called the nuclear force. All the interaction going on inside the nucleus has nuclear force and as well as electromagnetic force, because you mentioned proton carries charge. As long as you completely forget about the electromagnetic interaction, that means no charge needs to be talked. We don't have to talk about charge. We can roughly say that neutron and proton are the same, because then the only thing that is differentiating neutron and proton is the mass difference. But we can see that their masses are roughly exactly the same. So if their masses are the same, if we forget about the charge, approximately they should be exactly the same particle. But again, you are right, they are not the same particle. This is an approximation. When you make this approximation and try to explain only the nuclear system based on nuclear force, you will see that the theory that we talked about is good up to a is approximation up to a very good approximation. But whenever you talk about the exact mass splitting between them, whenever you introduce the corresponding charges, you are right, they are not the same particle. And I'm going to talk about they are not the same particle a little bit later, but we didn't know it before, okay? Just based on this simple analysis, we can see that approximately we can explain their theory by a SU2. But this SU2 is actually describing the nuclear system. But later I will show you this is not correct. We need more accurate thing. So everything so far I talked about is just an approximation, and it holds to a very good approximation. That's the point. Does it answer your question?
Okay, thank you, Dr. Saad. Thank you very much.
Yeah,
for the
okay,
answer.
And I will get back to you. Okay, they are not the same particle, and I will talk about it. Okay, thanks.
Okay.
What is the other question?
Just two so far. You can go ahead, Saad.
Okay, I can go ahead. Okay, so as I describe everything, so these are approximate things, but we actually need to talk about more exact thing. And that's for that purpose, we need to talk about a little bit more about group theory, okay? So far I only talked about SU2 group. And as I convinced you, to describe the interaction, we need gauge boson or the force carrier. And for SU2, these gauge bosons can be only triplet, or at least this is what we see in our nature. As I described, these are already experimentally proven. Okay, so we only see triplet. So I am talking about a standard model, and we will see that in the standard model, there are 3 gauge bosons associated with SU2. And we also need to talk about SU3, but since this is a bigger group, you can do a simple calculation and you can show that 3 square minus 1 gives you 8. It must have 8 force carriers. And these 8 force carriers are called the gluons. And I'm going to talk about it. Okay. So if I combine everything and try to explain our nature, the theory is called the standard model. And this standard model is nothing but group theory, because I already convinced you everything we see in our nature, it is experimentally proved that group theories hold. So how do we explain standard model? By a combination of 3 different groups. One is a U1 group, a very simple one. One is a SU2 group, another one is a SU3 group. Each of these groups have different force carriers. So as I already explained, since this is U1, it can have only 1 force carrier. which is again not exactly the electromagnetism because it's more involved and I don't want to talk about it. There is a different U1 which comes whenever the symmetry is broken. I'll talk about it later. But that U1 is associated with just one force carrier, which is called a photon. So that corresponding force is nothing but electromagnetism that we already know. And all the particles that carry a charge, they will feel the force because we know that any charged particle definitely interact via the electromagnetism. Now let's go to this SU2. As I discussed, this SU2 must have three force carrier. In the standard model, we call it the W boson and the Z boson. Z boson doesn't have any charge. W boson have plus minus charge. And I'm going to talk about it. Quarks and the leptons, they actually have these SU2 charges. So this new force, which we call the weak forces, must be filled by these forces. Finally, there is SU3. And as I just discussed, since it is SU3, it must have 8 gluons. So the force carriers are the gluons. And I'm going to talk about it. Any particle that carries some charge under this SU3, that charge, we call it the color. So any particle that carries a color must feel this force, and we call this force to be the strong force. So if all these forces are experimentally verified, so this is why the standard model, which describes our universe, consists of 3 different types of forces: a strong force, weak force, and a combination, which is the electromagnetic force. So this is the summary of the standard model's force carrier. What about the fermions? As I discussed some time ago, in the standard model, there are 2 different types of fermions. One types of fermions, those are called the quarks. Why they are called the quarks? Because they carry color. That means they are charged under this SU3. So this is why they are called quarks. There are other types of fermions. They don't have any charge under this color. So these are color neutral. And this is why we call them leptons. And in the standard model, there are 2 different types of leptons. One, they don't carry any electric charge. That's why these are called neutrinos. And the electron, which carries 1 unit of negative charge, we call it electron, and it's a lepton because it doesn't carry any color. On the other hand, there are 2 different types of quarks. We call it the up quark and the down quark. Up quark has a charge of 2/3. Down quark has a charge of -1/3. Now let's get back to the question you were asking. Proton and neutron, they are not the same particle. In fact, they are not the same particle because we have already experimentally proved that proton is not a fundamental particle. So the theory that I explained before, that was an approximate theory. So if you remember the question you were asking, this theory I talked about, this is an approximate theory, but a true theory is proton is not fundamental, but it is made up of fundamental particles, which are quarks. So a proton is made up of 2 up quarks and 1 down quark. And as you see, up quark consists a charge of 2/3, down quark consists of -1/3. So if you sum them up, you get 1 unit of charge. So this is why proton contains 2 up quarks and 1 down quark. Neutron is a completely different particle. It is not the same as proton, and it consists of only 1 up quark, but 2 down quark. And if you add the charges, you will see that it's a neutral particle. So again, neutron is not a fundamental particle. It has 0 charge because 2/3 -1/3 -1/3 makes it a 0 charge particle. And this is exactly how they behave, is exactly described by this SU3 group. and which is again experimentally very well proven. So everything I'm talking about are already experimentally well proven. One more thing, since I described, they actually carry color because this is SU2. Any charge under, sorry, SU3, any charge under SU3 is called color. And there are three different colors: blue, green, and red. These are charges. Okay, these are not exactly color that we see. These are some kind of more complicated thing, but we actually describe in terms of color. But the main important thing is we see proton, but whenever we see proton, we don't see any color. Why is that? Because it has three different quarks with three different color. Once you combine these three different color, it becomes colorless. So as a result, we see proton and it doesn't carry any color. Blue, red, and green makes it a color blind. Exactly the same thing here. They always come in a combination where you see colorless particle in our nature. Any question?
Any question? Please raise your hand.
So let me clarify. These are colored. These are not the color we see. It's a charge. So it's a different kind of color charge I'm talking about. Okay, so please don't get confused about it.
Go ahead, Saad.
Okay, so if there is no question, let me go ahead. So this is exactly what I was mentioning. In the standard model, there are two different types of color quarks, up quarks and down quarks. Up quark, and there should be three different types of color because this is SU3. So these three, meaning this up quark should separately be a triplet, meaning it should come with three different color, as I already explained. Similarly, down quark must also be a triplet under SU3, so it must come with three different color. Let me go to SU2. Because the standard model contains this SU2. Under this SU2, since this is a two-dimension, the quarks and the leptons are charged under this SU2 and they must form doublet because two, everything related with two, we call it doublet representation. Everything associated with three, the fundamental representation, we call it a triplet. So it's a combination of three different states. It's a combination of two different states. So for a quark, left-handed quark doublet, it consists of one up quark and one down quark, meaning they are also charged under SU2, not only SU3, they are also charged under SU2. But the leptons, such as we talked about the neutrino and the electron, they form a doublet. They are charged under this SU2, but they don't carry any charge under this SU3 because they are color neutral, and so on. And then there are some additional fermions. They don't carry any color under SU2. That's why we call the singlets. Okay, that means one. Singlet means one, doublet means two, triplets means three, and so on. So let me proceed. So what does it tell us? Few minutes ago, I told you anything that is associated with SU2 feel the weak interaction, and as a result, their interactions are mediated by the force carrier, which are the W bosons. On the other hand, anything which is SU3 feel the strong interaction, and their force carriers are basically the gluons. And this is exactly what we see here. Let's talk about the quark doublet. As I mentioned, a quark doublet consists of an up quark and down quark. So their interaction must be mediated by W boson because this is a SU2. And for SU2, we have seen the force, one of the force carrier is W minus. So what is the interaction? How they are interacting? You see, up quark is coming, which has a 2/3 charge. It is interacting or absorbing a W minus gauge boson or force carrier, and this one -1 and 2/3 is becoming a -1/3. So it is converted into a down quark. So you can always change a up quark into a down quark. by the interaction of the W force carrier. And the same thing is happening for the lepton, because lepton is a doublet. It has a neutrino and an electron. So a neutrino is coming, which does not carry any charge. It is interacting with the force carrier W minus. It is absorbing it. It is becoming an electron. So charge is conserved. For all processes, charge must be conserved, and which is also experimentally proved. Let's talk about SU3. As I mentioned, for the SU3, there are different colors. So one color can go into another color, or this color can go into another color. How? It is SU3. So the force carrier must be the gluons, right? I talked about it. So let's say an up quark is coming. It is which has a color of red. And then it is absorbing a gluon, which is carrying an anti-red color and a green color. And that's why a red-green color is cancelled out by the anti-red-green color. Only the, anti-red color. So only the green left. So one up quark having a specific color can become another quark having a different color, because it is completely mediated by the corresponding force carrier, which is described by SU3. So all I described about so far are the fermions of the standard model, which are basically spin half, and the force carriers, which are spin 1. But I also mentioned that in the standard model, one must also have spin 0 particle, which are called the Higgs boson. Where is it? So this is the last piece of the standard model, which actually the journalists call the God particle. And it appears that even though we have discovered all these fermions and the force carriers a long, long time ago, only just recently we have discovered this Higgs boson. So this is the news which came out in 2012. And as a result, they
know that this is not the true God particle, right? It's not intended to be God particle. It was initially called goddamn particle. So totally different meaning.
Right. So yeah, so this is nothing to do with God. Okay, so yeah, let me clarify. It is nothing to do with God. It's just called a God particle. But the point is, this is the last thing that we just recently discovered in the it's a very, very large experiment, which is called the Large Hadron Collider, LHC, which discovered this last piece of the standard model. We call it the Higgs boson. And as I described, it must have a spin 0 particle. And as a result of this discovery, Englert and Higgs, they got the Nobel Prize in 2013. So this actually completes the standard model. In the standard model, we have fermion. We have observed all the fermions. We have force carrier, photon, gluons, W boson. We have observed all of them. We have discovered all of them. And finally, the Higgs boson, we have discovered everything. So then the natural question is, why we really need this Higgs boson? And the answer is actually very, very important, which is Higgs boson is actually required to break the symmetry, some part of the symmetry of the standard model. Once this symmetry is broken, it gives us the known force, which is the electromagnetic force. And in our everyday life, we observe the electromagnetic force. So how this symmetry is broken, I am not going to talk about it. It's more mathematics, more details I'm not going to talk about. But the most important thing is, whenever this Higgs breaks the symmetry, it gives masses to the SU2 gauge bosons that we talked about. At the same time, it also gives masses to all the fermions. And if since we have fermion masses, we have masses, such as electron has a very specific mass, up quark, down quark, they have very specific mass. If we would not have this specific mass, our universe would not exist and our life would not exist. So Higgs is a very, very important element of the standard model. And we finally realized that it exists. And currently, we are measuring its properties at this LHC. And so far, everything is very consistent. So we know that standard model is a very beautiful theory. Despite of the fact that standard model is an extremely good theory, extremely precise, it precisely matches with all the experimental observation. Mathematically, it's a very beautiful theory. There are some problems. Let me just charge my laptop. So far, any confusion? Any question or confusion?
Any question? Please raise your hand. Or if you want to clarify something, go ahead.
Probably no. Okay. Okay. So the point is that even though the standard model is a great theory, there are some problems with the standard model. Okay. What are the problems? I listed a lot of them, but let me talk briefly. Okay. First thing, as I described in the last one here, even though Higgs gives masses to all the fermions, it does not give mass to the neutrino. Okay, this is one important point. So in the standard model, neutrinos are still massless. However, experimentally, neutrino masses has been measured. Okay, not exactly measured, but we know that neutrinos oscillate, which clearly tells you that neutrinos must have non-zero mass. So this is one major problem of the standard model. We cannot talk about how neutrinos mass come from. And there are lots of theories to extending the standard model, how their masses can be described, such as Giulio has several works, right? Giulio has several works, so you can go ahead and look at his works. Okay, so Giulio has several theories how to explain the problem of the standard model and how you can give masses to the neutrinos. So if you have more details question, just ask Giulio. He's the neutrino expert. All right, what are the other problems? So we have so far talked about particles. Every particle comes with an antiparticle, but it appears that in the universe, we realize that our universe is matter dominated. We very rarely see antiparticles. So we have very less amount of antiparticles. We can create the antiparticles in the experiment, but in the entire universe, we have very less amount of antiparticles, which is known as the matter-antimatter asymmetry. Why is it? We don't know. And a standard model cannot explain it. So this is another major problem of the standard model. Another major problem is we know that our entire universe is a large portion of it, about 30%, okay, sorry, about 25% of our entire universe is made up of dark matter. Okay, so about 30% is made up of matter, but only 20% of this 30% is made up of the matter we know, such as ourselves, galaxies, stars, and everything. It is only a small fraction. And of this matter, about 80% made up of dark matter. And a standard model cannot tell us what dark matter is. So these are major problems, and standard model cannot give us any idea. So the question is, how do we solve these problems? Well, probably a natural choice to solve this problem is to extend the symmetry of the standard model. As I described, the standard model consists of SU3 cross SU2 cross U1. But maybe we need to extend the symmetry to a bigger symmetry, and it will explain it. Then you can immediately ask the question, why do I need to extend the symmetry? And the reason is we have some indication. What is that? As I discussed, a standard model has 3 different groups. Each group describes a different force. SU3 describes color. How strong this color interaction is described by the associated coupling constant, which is denoted by alpha 3. Again, this SU2 describes a different force, weak force, and the corresponding strength of the force is called alpha 2. Similarly, this U1 is another force and the corresponding strength we denote it by alpha 1. These are called the coupling constant. Even though we call it constant, these are actually not constant. And the point is, experimentally, we have proven that if you change the energy, their values change, which is experimentally proved. And the change is something like that. So along this y-axis, I show you the strength of this force. Along the x-axis, I show you the energy. As you increase the energy, you see that the values are changing of these couplings. And if you go higher and higher in energy, you see that in the standard model, they try to meet at a certain point, but they don't quite meet. But in any case, it tells you that they are trying to unify at a certain point. And in fact, if you increase the symmetry of the standard model, a very simple example is basically supersymmetry. You see that at a very high scale, they immediately meet. That means all the forces are unified. Since they meet at a single point, it means that there is just one force. All the forces we see in our nature must come from a single force, and this is called the unification. So our nature probably telling us there must happen some unification, because experimentally we see a similar behavior of these coupling constants. So this is why unification is really, really important. So what is grand unification? This is grand unification. We know at the very low energy, we have electricity and magnetism. And at first we thought they are different forces. But Maxwell showed us they are not different forces. You can unify them into electromagnetism. So they are exactly the same, one single force. And then today I also talked about a strong force which is happening inside nucleus. There is weak force associated with the SU2 and so on. As you increase the energy, these coupling constants make them unify. And at a very, very high scale, all these forces will unify and they will come from a single force, which is called the grand unification.
There's a question from Professor Gunara, please.
Yes.
Go ahead.
Yes, thank you. First of all, you said that the standard model is a good theory, but there are some flaws. Okay, there is some loophole.
Yes.
For example, if we extend the standard model to the GATS model,
yes,
is it the GATS model so far? There are several models, I think, SU5 and SO10, I think, yeah.
Yes.
Yeah. How about this grand unification theory does it solve some of these problems in standard model, or they just extend the problem?
Yes, so you actually asked an excellent question, and this is exactly what I'm going to. This is exactly the direction I'm going. Okay, so as you already mentioned, standard model has several problems, and I listed many of them here. And now I'm talking about that to solve this problem, we should go towards grand unification. And then I will show you, whenever I go to grand unification, they are going to actually solve the problems that we see in the standard model. So the answer to your question is yes, and I'm going to talk about it right now.
Okay.
Okay, great. Thank you. Any other question?
I also have another question.
Okay,
also.
Yes.
Okay. So the electroweak interaction, basically, I mean, the coupling is not really unified at some point, right?
Right. That is correct.
Yeah. But how this GATS model also solve this problem? I mean, is it also unified at some point, for example, in electroweak interaction, or these three couplings also unified at some point in God's theory.
Yes, yes. So what you said is exactly correct. So whenever we are talking about the standard model, as you are right, it does not actually unify the these two different couplings, this SU2 coupling and U1. You have to run up at some point to have a unification. And again, if you run up, all these three couplings will unify. And this is exactly what is done in GUTS. And this is exactly, again, what I'm going to talk about in more details. So you are right. What you said is exactly correct. But I'm going to talk some very simple examples, but I think that will clarify your also the question you're asking. So let me proceed. So the last two questions that I found, I'm going to talk about it, but if something is not clarified, ask me again, I will answer. Okay?
Okay.
Okay, so the question is, so now as I already convinced you why we need to go towards the grand unification, let us talk about what is actually grand unification. So as I already discussed, grand unification is basically nothing but a bigger symmetry, but starting from the standard model. So the first obvious question is, what is the minimum bigger symmetry that can contain the standard model? So what is the standard model? SU3 cross SU2 cross U1. And it turns out that group theory already tells you SU5 is the minimum possible single group that contains the entire standard model. Then you immediately get lots of answer. Since this is a single group, it has a single force. All the forces in the standard model are unified because one group can give you only one force, right? So SU5 has a single force and it will describe that at some high energy, all the forces we see in the standard model are unified into a single group. As energy is decreasing, it will break down to a standard model. And as a result, as we go smaller and smaller in energy, the group is breaking down to smaller and smaller in group factors. And as a result, at the low energy, we see different groups and we see different forces. But at the very high energy, everything was unified. So this is the main concept of grand unification. So the most simple example is nothing but SU5. And immediately you see that the minimum amount of representation, we already talked about doublet, triplet, and so on. But since the minimum representation one can have is 5, it's called the fundamental representation. And the amazing thing of this grand unification is this 5-dimensional representation unifies part of the quark and the leptons that we already talked about. As we already discussed, this neutrino and electron, they separately form a SU2 doublet. This down quark of 3 different colors separately form a SU3 triplet. But amazingly, now we have SU5, it unifies both the leptons and quarks into a single family. So this is the beauty about the card. Not only it talks about a unification of all the forces, it also unifies the quarks and the leptons. So then you can ask about, okay, so we already know what are the force carrier of the standard model, but now you should have more force carrier because of this unification of the quarks and the leptons. And what are the new force carrier? You see that since now they are contained in the same representation, a down quark can go to an electron. How? By the new force carrier, we call it Higgs boson, which carries a 4/3 electric charge. So you see electron is coming, it is absorbing a 4/3 X guy, and charge conservation will automatically tell you that only possible way it can go into a down quark. And the other thing is we also know neutrino. So down quark can also go to a neutrino, but another force carrier, which we call Y, that must carry an electric charge of 1/3. Then the other question you can ask, what about the other quarks we have talked about? We know there is up quark. Where is the up quark? Answer is here. Once we know the 5-dimensional representation, from this 5-dimensional representation, you can do a little bit of group theory. I'm not going to talk about 5 cross 5. It will give you a 10. And then it will form a 10-dimensional representation. But the end point is all the fermions that we talk about in the standard model are unified into a 5-dimensional representation and a 10-dimensional representation. So rest of the fermions that we know in the standard model are contained in this 10-dimensional representation. And since it's a bigger theory, it's a SU5, there are new force carrier, and they tells you how one color of up can go to another color of up, electron, how can go into a up quark, how down quark can go into up quark, and so on. All these are precisely described by SU5 group theory. Then the next question is, what is the consequence? Since we made the symmetry bigger, what is the consequence it gives us, or what is the new thing we have? Well, it tells you that the protons that we know of will decay. In the standard model, protons are completely stable. If you have a free proton, it will always remain free forever. I mean, it will never decay. But once you extend the theory, it tells you proton mass decay, which tells us we are all going to die at some point. No matter what, because we are made up of protons and neutrons. If the nucleons decay, we are going to die, right? So the question is, how do they decay? As I just convinced you, a down can interact with the X gauge boson, and it can be converted into an electron. And similarly, one color of up can convert it into an anti-up quark by the exchange of the same gauge boson. So, which actually makes a proton turning into a pion and an positron. So proton must decay into a pion and an electron. This is not electron, this is the antiparticle. So this is the positron. Okay, this is positively charged. So the main consequence of guard theories is proton mass decay. But you can do a lots of calculation I'm not going to talk about, and you can try to calculate what is the lifetime of the proton. It appears that the lifetime of the proton depends on the mass of this heavy particle, this gauge boson. Higher the mass, bigger the lifetime of the proton. And it appears that we have been searching for proton decay in the experiments for a very, very long time. For the last several decades, it's about 30 years or so, we have been measuring it, and so far we have not seen it, which tells us that the lifetime of the proton must be somewhat greater than 10 to the power 34 years, which tells us that this grand unification must happen at a very, very high energy. So of course, eventually we will all die, but not so fast. Protons are not going to decay so fast. We are still waiting to observe when the proton is going to decay. It's a very important experiment, and we are going to find out soon. Okay. So then some of the people actually ask the question, so what is the advantage? Well, there are lots of advantages of the SU5 guard over the standard model, such as it unifies the quarks and the leptons. And most of all, in the standard model, why charge is quantized, we have no idea about. Theory doesn't tell you why charge is quantized. But since SU5 is a unified theory, okay, it's more details. It has some generators I'm not going to talk about, but it exactly predicts that charge must be quantized. First of all, it unifies all the forces. And in some version of the theory, it can gives you dark matter and so on. So that's all about the SU5. However, SU5 is a good theory we have seen, but it also has some problems whenever we talk about the minimal SU5 guard. What are the problems? Let me talk about a few, such as in the minimal SU5, neutrinos still remain massless, so which is not good. Another thing is proton is actually decay so fast, but we have not experimentally seen it. That means minimal SU5 is not a good theory. And there are more problems. I'm not going to talk about it. But the main point is, it means maybe we have to extend the symmetry into a further bigger symmetry. What is the next candidate? Probably SO10. Someone already has mentioned SU5, SO10, and so on. Probably the most elegant candidate is the SO10 grand unification. Why is that? The first reason is, if you remember, whenever we talked about SU5, the fermions were not fully unified. It has a separately 5-dimensional representation and 10-dimensional representation. So there are two different disjoint representations that contain all the fermions in the standard model. But in SO10, the amazing thing is it has just one representation, which is the 16-dimensional fermionic representation that contains all the fermions that we know in the standard model of a single generation. All the leptons, that means neutrino, electron, all the up quarks of different color, all the down quarks of different colors, and they are antiparticles. All the particle, antiparticles, everything is unified into a single representation. And more amazing thing is, on top of it, on top of all the standard model fermions, it also contains a new fermions that is not in the standard model, which is the right-handed neutrino. Because in the standard model, we have neutrino, which is the left-handed neutrino. There is no right-handed neutrino. This SO10 in the single representation contains a right-handed neutrino. As a result, it gives us neutrino mass. So this is the most amazing thing about SO10. It automatically tells you, since it must contain the right-handed neutrino, neutrinos must be massless. So this is an amazing prediction, which matches with experiments. Also, all the fermions are unified into just one representation. It unifies all the forces into a single force. And another amazing part is the same right-handed neutrino that we talked about, which gives the neutrino mass. It is very heavy, typically, it's very heavy. And when it decays, it solves the matter-antimatter asymmetry. So this is amazing. Furthermore, in SO10, the unification scale is much higher than SU5. So proton decay, the lifetime of the proton decay can be easily extended. And that is completely consistent with our experimental measurement. And there are some extension of this SO10 where you can also incorporate the dark matter. Is there a question? I'm sorry. Okay, so
no question so far.
Okay, good. So one can also incorporate this dark matter and so on. And one more important thing, I have already discussed about the fact that whenever we talk about grand unification, the unification scale is very, very, very high. But the low scale is actually about here. So there is a huge difference in the energy scale. If we have SO10, the entire energy scale, many interesting physics may happen. Okay, it's not so boring. For SU5, it's a little bit boring because we only have the unification scale at the very, very high scale, and then the standard model at the low scale. But if we have SO10, you can ask the question, so if we have SO10 at the very high scale, how do we get to low energy standard model? Well, many different interesting things can happen. SO10 can break down in many different groups depending on how the Higgs representations are, I'm not going to talk about it. But the point is, many different interesting physics can happen in between the very high scale and the standard model. Finally, we reach the standard model. And then this standard model is breaking down to the lowest scale, which we already know, the color group and the electromagnetic force. So this is the basic concept about what standard model is. What are the problems of the standard model? Why we need to extend it? What is the natural choice? And as I explained, the natural choice is the grand unification. Once we have the grand unification, what are the candidates and how can they solve all the problems we see in the standard model? But more details are actually technical. So I gave you a link. You can actually click on this link. It has all the list of my work. So I have several works on grand unification. So here is a list of my works related with SO10 and SU5. There are more works. You can just look into it, but all these things are very, very technical and I cannot talk about in this colloquium. But the point is, I just wanted to convince you that unification is a very important concept in our nature, which has been proven in many, many times because Maxwell unified electricity, magnetism to electromagnetism, and so on. I'm not going to talk more details into it, but in the end, we may see grand unification, which has not been proven yet. Lots of experiments are going on. Standard model is a very, it's a very good theory. It matches everything with the experiment's prediction. However, it has some limitations. We need to extend it, and the natural choice is grand unification, but it must be proven. So far, all the grand unification I talked about, these are still theory. We are working on lots of experiments. At some point, we may see some experimental evidence, and it will actually tell you whether grand unification is correct or not. So that actually ends my talk. So thanks for listening.
Okay, let us give applause for Saad for very nice talk. And there is one question from Professor Gunara. Please.
Okay, thank you. Very interesting talk. First, I have a question about how this SO10 GUTS model predicts the lifetime of the proton.
Okay, so again, this is a very good question, but the answer is actually very much involved. So let me tell you a little bit more about it. So whenever we talked about this SU5, I mentioned that roughly speaking, the lifetime of the proton is given by just two parameters. One parameter is what is the mass of this gauge boson, and another one is this alpha, and this alpha is actually nothing but this unified scale. Whenever all the forces are unified into a single force, what is that value? So the question to your answer is this. Once we know SO10, we need to find out exactly at what scale the all the gauge couplings are unified. So that scale will actually tell you what is the mass of the gauge boson. And at that scale, we need to actually find out what the value of this coupling constant. Once we know these two, it will tell us the lifetime of the proton. Naive estimation will actually tell you the lifetime of the proton is about 10 to the power 34. But SO10 is not that simple because I was showing you, you can break it in many different ways. Depending on how you break it, the GUT scale can be different. If the GUT scale is different, the mass of the gauge boson is different, and correspondingly, the lifetime of the proton is different. So the answer to your question is, naively speaking, 10 to the power 34, but you can make it bigger. but that requires a lot of more calculation, and I am not going to talk about it. But yeah, you can exactly determine. And this is exactly what we do. Okay, if you actually look at my works, we do exactly the same thing. Okay, but it's a very good question. Does it answer your question, by the way?
Okay, thank you. The second question is about, so in SO10 GATS model, is it the left-handed neutrino are still massless, yeah? Or we could also, I mean, from the parameter in SO10 model, is there, we can give a mass to the left-handed neutrino, since according to recent observation from cosmic neutrino, there might be that this left-handed neutrino should be massive.
Right. Yes, you are right. You are 100% right. Actually, neutrino, the concept of neutrino mass has been verified in around 1998. Julio, is that correct?
Yes. Okay,
yeah. So actually, around from 1998, we already know that neutrino mass must be massive. And as you discussed, yes, in the SO10, neutrinos must have mass. These left-handed neutrinos must have mass. And the reason is that it is associated with an anti-neutrino, or simply we call it the right-handed neutrino. Due to the presence of these right-handed neutrinos, these left-handed neutrinos automatically have mass. You cannot make them massless in the minimal theory. They are massive. And this is why SO10 is one of the most elegant theory, because it automatically tells you that they have mass, and which exactly matches with our experimental observation, as you pointed out. Does that answer your question?
Yeah, partially, but okay. Okay, maybe okay. There are so many questions comes out of my mind, but I think we should ask other participant to ask the question, I think. Thank you.
All right. Now,
thank you very much.
Okay. Firdaus, yeah, Firdaus, he wants to ask a question. Go ahead.
Okay, thank you. Can you go to slide 40?
Yes.
About Feynman diagram of proton decay. Yes. Is it quark-down or anti-quark-down?
I'm sorry, the question is whether it is proton or anti-proton.
Yes.
Okay.
Is it quark-down or anti-quark-down?
Okay, so the answer to your question is, in this diagram, I am showing proton, but it doesn't matter. I mean, whatever happens for proton also happens for the anti-proton. But you are right.
He's asking whether this is down quark or anti-down quark. Is that your question?
Yes, yes.
Yeah, whether this is down quark or anti-down quark.
Oh, this one is actually down quark, because I am actually talking about proton. So let me just again go back to here. So if you remember, a proton consists of 2 up quarks and a down quark, not an anti-down quark. All of them must be quarks, which will give you a proton, or all of them must be anti-quark, which will give you an anti-proton. You can talk about either of them, doesn't matter. So let's choose, I want to talk about proton. So it must be up quark, and down quark, not their anti-particles, right? So in this Feynman diagram, I have shown everything quark, quark, quark. But then this quark is converting into a positron due to this gauge interaction. This up quark later is then converted into an anti-up quark. And then this up quark is just going. So since we have an anti-up quark in the final state, this anti-up quark together makes a meson. So does that answer your question?
But quark-down have minus 1/3. Is it right?
Proton has charge +1, right?
Yes, but quark-down have minus 1/3 charge, electric charge have electric charge is -1/3.
Yeah, the electric charge of the down quark is -1/3.
Yes,
Yes.
yes.
What was
Yes.
the problem?
Let me, sorry.
Are you asking about the charge flow?
Yeah, so maybe actually show you here. So up quark has a positive 2/3 charge. So there are two up quark charges. So you have 1/3 charge, but it consists of one down quark charge, which is -1/3. So that will cancel these two contribution. Sorry, why?
Yes.
Oh, I see your question.
Yes.
So, okay. So I think I am calculating it in the wrong way. So 2/3 and 2/3 will make it what? 4/3, right? So 4/3 and then -1/3 will give you +1. Does it make sense? 2/3 and 2/3 gives you 4/3, right? And then you subtract -1/3 from 4/3, you come up with +1 for the proton. Does that answer your question?
Does it answer question, Firdaus?
I feel confused because boson X have electric charge is 4 divided by 3.
4/3.
But
4/3, yes, 4/3. Yes.
But charge of positron and down quark, if we sum of them is 2 divided by 3. That's different. That's different electric charge.
Are you asking about the charge flow? Saad,
Yes.
He's asking about the charge flow. Maybe you can tell that the Feynman diagram that you just showed is going from down to top.
Okay, yeah. So for example, if you consider this Feynman diagram, I am considering that fermion is actually going in the upward direction. Okay, yeah. So Julio already pointed it out. So you see that -1 charge is moving in the upward direction, and then it combines with a 4/3 charge, and then you end up with positive 1/3 charge. So it is moving in the upward direction. Okay, now I am not going towards this direction, that direction, or any other direction. Simplicity, just consider this way. Does it make sense?
Okay, I got it. But the second question,
yeah,
about model standard. The standard model has many problems. The standard model has many problems, such as not accommodate dark matter,
yes,
neutrino mass, and so on. Why was the standard model not updated until now? Why was the standard model not modified until now? What is the reason? Thank you.
Okay, again, this is a very good question. So standard model has been modified, but that's from theory, right? That's what I wanted to explain in this talk. All these modifications, such as these SU5, SO10, and everything, these are just theoretical proposals. And people have been working on this modification of the standard model from last 40 years or so. Okay. But the main question is this: why we are so adamant about standard model? And the reason is that all the experiments that we do exactly matches with the standard model. Besides, of course, besides this neutrino mass, no dark matter, no matter-antimatter asymmetry, if you forget about these few things, there are many things standard model predict, which I haven't listed here. There are thousands and thousands processes standard model predict. All those thousands and thousands processes exactly match with the standard model. So a standard model is an excellent theory. We cannot downplay it. But of course, a standard model needs to be modified because of these problems, and people have been, all the scientists have been modifying it, but all these new modifications, none of them has been experimentally verified yet. So these are just theories. This is a very important thing to keep in mind. Only a standard model has been verified by experiment. Any new modification, new addition to standard model must be experimentally verified, which we have not yet. So there are millions of different new theories. We don't know which theory is correct. We know a standard model is correct. But what is the extension? I don't know.
Yeah, Saad is one of the people who work on the modification of the standard model, right, Saad?
Oh, okay.
with his grand unified theory. Okay, better move on to another person. Bayu, go ahead. Bayu Dirgantara, ask your question.
Thank you for a very interesting talk. I would like to ask about the unification scale of God. Is there any God theory that predict the unification scale is around the Planck scale? Why not in the Planck scale, or why not in the Planck scale? Is it related to the lifetime of the proton, or so the scale is down to the 15 GeV?
Okay, so this is an excellent question. Yes, you are right. So typically, whenever we talk about, let's say, SU5 grand unification, it is very hard to get a unification at a very large scale. So what is the reason? Because as I discussed, these alpha 1, alpha 2, alpha 3, these are the gauge couplings of the standard model, and they has been experimentally measured. We know exactly what is the value at the lowest scale for alpha 1, alpha 2, and alpha 3. And then we start to run in the upward direction. How do they run in the upward direction? Depends on the grand unified theory, as you already pointed out. So where exactly they are going to unify depends on the theory. If you start with SU5, you cannot go too high, above 10 to the power 15. So this is why SU5 is not a good theory. Of course, you can make it complicated and make it high, but it's difficult. But if you go to SO10, you can go up to, let's say, about 10 to the power 16 GeV. But again, if you sufficiently make it more complicated, you can in fact go up to Planck scale. You are right. But it becomes a non-minimal theory. It's not that motivated, because we always try to build minimal theory, because minimal theories give you prediction. So the answer to your question is, it is possible, but for a very complicated theory. We don't want that. You can go up to Planck scale.
Okay, last questions. Can you go to the 5-bar plate of SU5?
Yes.
5, yes. This technical question actually. Why the bar only apply to the SU3? Why not both the SU2 of lepton?
Right. So it's actually a technical question, and I am not going to talk about it. But I can tell you how to answer it. Okay. So as I discussed, so SU5 is a bigger group. It means it contains more number of generators, because since you are asking a technical question, so I definitely assume you already know about the generators. So SU3 has certain number of generators, SU2 have generator, U1 has generator. So whenever you are embedding this group inside SU5, these generators must obey some kind of relationship, and that will actually also tell you how charge is conserved, or more precisely, how charge is quantized. So if you do a proper calculation, it will immediately tell you this is the only possible assignment, because if you sum over all the charges for a representation, it must be 0. You know, down has a charge of -1/3, but I added anti-down. So it has a positive 1/3 charge. So 3 positive 1 charge will give you 1 unit of charge. So you cannot use E plus, you have to use E minus. Otherwise, summing over the charges will not be 0. And this is not a correct mathematical theory. So it's more related into generators, and I don't want to go into details, but it's a very good question.
Yeah, I see. Thank you.
Any question, Bayu? Are you happy with that?
Very happy. Thank you.
Okay, we move on to Renat.
Thank you. So you claim in, I don't know, like slide 45 or 44, something like that. Yeah. So now the one before, I think, yeah. So you said that the existence of dark matter doesn't require additional symmetry, but well, at least from I see that the SO10 model doesn't have dark matter. I don't know how would you incorporate the dark matter into that picture, and yeah, can you elaborate this additional symmetry statement? Thank you.
Okay, sure. Okay, so again, this is a very good observation. Yes, you are right. If you just look at the minimal particle content of the SO10, you are right. There is no dark matter candidate, 100% correct. But in general, you can actually extend the, let's say, fermionic content or the scalar content of the theory, and you can have a new dark matter candidate. So it's an extension of the SO10. But the main point I want to mention here is this. Typically, if you just start with a standard model, and if you by hand add a dark matter, it does not become a dark matter unless you add some additional symmetries by hand. So which is very less motivated.
Right.
But the excellent part about SO10 is if you add a dark matter particle, you can show by calculation that SO10 inside SO10, it contains a symmetry. Okay, it's a Z2 symmetry. What is Z2? I don't want to talk about it. It contains a Z2 center of the model, which can automatically stabilize the dark matter. So this is an amazing thing about SO10, not realized in SU5. SU5 does not have it. SO10 automatically has it. So this is a very well motivation why one must have SO10. It automatically stabilizes the dark matter. Since dark matter are stable particles, you must require some symmetry. SO10 automatically provides you the symmetry. That's my point.
So there would be like an accidental Z2 symmetry or something like that?
Exactly.
Or,
this is from SO10, it is not exactly accidental. It is something called the matter parity.
Okay.
Yeah. So if you actually look at, if you actually look at how, say it again.
It's not U1 like some U1 number.
It's actually a Z2 center of SO10. So it's a built-in matter symmetry inside SO10. It's a very special property.
Yeah. Never work in this GAT or SO10, so I have no idea. So, but okay, that's good. Thank you.
Yeah, thanks.
Okay, another question is from Patipan. Go ahead, Patipan.
Hey, Saad. First of all, thanks for the very nice talk. So maybe I have a question on this slide as well, but probably not this slide, but the one before when you list all the flaws of the standard model, right?
This one?
No, the standard model is good, but flaw theory.
Okay, so this one.
Yeah. So
yes.
So I have a question about the item that you said charge quantization is not realized, and can you elaborate on that, and how does unification help with charge quantization?
Okay, so excellent question.
Because I just want to know your take on this.
Okay, so so you asked a very excellent question, but again, it's a technical question. Okay, so maybe I can try to answer it, but I'm not going to go into much detail. So let me remind you, a standard model has a group theory which consists of SU3 cross SU2 cross U1. And a few minutes ago, I was mentioning about the generators. SU3 has some generator, SU2 have generator, U1 has a generator. The problem with U1 is the charge assignments under U1 is completely arbitrary because it's a non-abelian theory. So the corresponding generator that you have, you can assign any charge you want. Doesn't matter what is the value.
Yeah, but we don't we need to have anomaly cancellation also? So it's arbitrary up to overall factor.
Yes,
right?
yes, arbitrary up to an overall factor, right? So the problem is this SU2 does not determine exactly what is that exact number. But the problem is that we have seen in the standard model, whenever you break down this SU2 cross U1, it must give you the electromagnetism, right? So since this part, of course, you are right, it depends on some gauge anomaly cancellation and so on, but it is not uniquely determined. As a result, what will be the charges of this U1 is not uniquely determined. There remains some arbitrariness. Even if you actually cancel some anomaly of a U1, you can have infinite number of possibilities. However, whenever we talk about a guard theory such as SU5, you see that this U1 generator must come from SU5. So this is no longer arbitrary. All the generators are coming from a simple group, which is a non-abelian group, which fixes some relationship among the generators. And this is why it automatically actually explains the charge quantization. So if you have any theory that contains an U1, charge assignment remains arbitrary. And we say that you don't understand the quantization. It can take any value you want. Once you are embedding into a simple group such as SU5 or any other group that does not contain U1, you exactly explain why charge quantization should be realized. Does it roughly answer your question? Again, it's technical.
So I think now I understand your point now. Yeah, thank you.
Good.
Okay, we still have a few minutes. Is there any more question just for one question? Please raise your hand or speak directly.
Can I ask again?
Sure. Go ahead.
Okay. Is there any possible to extend the theory beyond SO10, for example?
Well, yes. Yes, the answer is yes. But first, let me tell you why not. Okay. In general, you can see from SO10 that it contains all the fermions of the standard model of a single generation. So it's more elegant, it's nice. If you actually go beyond SO10, there are other bigger groups such as E6, E8, and so on, E8 cross E8. I don't know whether you have heard about string theory. So string theory typically comes from E8 cross E8, which is a very big symmetry. But the problem is there, you will get more and more fermions because bigger the symmetry, bigger the representation, they contain more number of fermions. So I don't know whether it's well motivated. You will get some fermions that are not in the standard model. These are new fermions. So some people say that, do you really need new fermions? Because we haven't seen them. So it's a choice. So since we have not experimentally measured anything, it's a choice. You can stay up to SO10. It's more elegant, it's nice. You can go to bigger symmetry, yeah. Yes.
Okay.
E6, E8, whatever.
Okay. Okay, just one more short question.
Yeah.
As far as I heard from the LHC experiment, that the property of Higgs particle somehow slightly different than predicted by the standard model, the property. Is it in SU5 and or SO10? I mean, this additional slightly modified Higgs boson could we explain this anomaly of this Higgs bosons? That's my last question. Sorry, thank you.
So that's a good question again. So again, before I answer your question, let me clarify one very important thing. So whenever we talk about the experimental measurements, And the anomaly that you mentioned, whether this anomaly is really an anomaly or not, that depends on the corresponding statistical fluctuation. If the fluctuation is less than 5 sigma confidence level, whether you are going to take it for granted or not, it's up to you, but some people say it's nothing because it needs to be proven. So proof requires more than 5 sigma. There are some small deviation with the standard model seen in the LHC, but those are all within only 2 sigma. So 2 sigma is a very small confidence level. You can take it seriously. It's up to you. Doesn't matter. So those are not really need to be explained for now. But to answer your question, yes, in general, it's possible. You can extend the standard model and try to describe those 2 sigma anomalies and so on. It is possible. But from grand unification, it is less motivated, because whenever you try to explain an anomaly, you require some particles at the low scale. Grand unification typically tells you most of the particles other than the standard model at the high scale.
Yeah.
So they don't really change the properties of the standard model. It is possible, but you have to extend it further. And I have not talked about it. Yes. So answer your question is, it is possible in an extended GART model. And also at the same time, experiments are so far in very good agreement with the standard model. A small 2 sigma discrepancy, they comes and goes, right? Julio knows more about it, right? They always comes and goes, but in the end, standard model is always winning. So far, there is nothing which tells us that a standard model is not good, unfortunately.
Okay, thank you.
Okay, one more question, Saad. There's a question from the chat room. How about the graviton? Can I have your comment on how gravity could be fit in the unified theory?
Okay, so let me clarify. So in this talk, I talk about grand unification. And the first thing about grand unification is we don't talk about gravity, because you see that I only talked about unification of the strong force, the weak force, and the electromagnetic force. We already know that in nature, there is one more force, which is the gravity, right? So if you try to actually also unify the gravity, you cannot do it in grand unification. You have to go to higher theories, which are typically known as string theory. And I have not talked about string theory at all. So the answer is no, it's not possible within grand unification, but it is possible within string theory, and I don't do string theory.
Okay, so that's the answer.
Right.
Is there more questions? I think it's already, the time is up now. It's already almost 4 o'clock here. So
I think there is a raised hand, or
oh, is there a raising hand?
Yeah.
Oh yeah, Prof. Hussein Halatas, please.
Yes. Thank you, Julio. Thank you, Saad, for a very nice presentation. I wonder, what about the Higgs mechanism in SO10 model? Is it also the mass of the neutrino generated via the Higgs mechanism? And if it is, then is there any number of Higgs should be exists?
Okay.
Or just a singlet? Okay, thank you.
Okay, so this is again an excellent question. So your question consists of 2 different parts. One part about the neutrino mass. So yes, I mean, neutrino mass is somewhat related to the Higgs mechanism, but it's a little bit different. Of course, 100% it is depends on Higgs mechanism, because whenever this Higgs mechanism takes place, this right-handed neutrinos gets a very large mass. As a result, this left-handed neutrino gets a mass by a mechanism which is known as the seesaw mechanism. And I have not talked about it, but it is in general related with the Higgs mechanism in some way. Okay, this is one part of the answer, but it's more elaborate, and Julio has Julio knows more than me about the type 1 CISO and neutrino mass, right? So let me not answer. But the other question you asked about the Higgs mechanism, yes, just like the standard model, how you break the symmetry, SO10 guard must also realize breaking of this symmetry by the Higgs mechanism. But unfortunately, since this is a bigger symmetry, you require more number of Higgs. What are the Higgses? For example, you can have a 54-dimensional Higgs, which will break the SO10 into Pati-Salam group. And then you can break the Pati-Salam group, for example, with a 126-dimensional Higgs. And finally, whenever you reach the standard model, you can break the standard model with a 10-dimensional Higgs. So all these are Higgs mechanism at different scales. So minimal theory contains at least 3 Higgs particles, 10-dimensional, 126-dimensional, and 54-dimensional. And then by Higgs mechanism, finally, you go back to our low energy standard model theory. And what Higgs you choose, yeah, it depends on your choice, but all of them are Higgs mechanism. Does that answer your question?
Yes, thank you.
Okay.
Okay, no more question?
Maybe I should make a remark.
Okay, sure.
Okay, yeah, just one remark, which is there are many things I try to answer in a simple thing, but all of them are extremely involved. So I try to avoid all the technical things, and all the technical things are actually addressed in my papers. So if you have any additional question, those you can consult my papers.
Okay, please check the link that he has given. I have one more question.
Okay.
I don't know if it's technical or not. Whether the scale of CISO mechanism
is
a clue for SO10 unification scale or vice versa. Can you comment on that? Can we have much lower CISO scale, for example, 10 to the 8 GeV?
Okay, so again, that's an excellent question. But the answer again depends on the model. Okay. So if we only consider the minimal SO10 model that consists of such as 54 or 45 or 210 representation to break SO10, and then it broken down further by 126 and finally by 10, you don't have any choice. Your right-handed neutrino mass or the CISO scale must be around 10 to the power 12. That is only possible scale because otherwise you cannot get the correct fermion masses, because you already know in SO10, all the quark, lepton, and neutrino masses are related with each other. So if you deviate this scale, it doesn't work. Everything is screwed up. So the answer is no, but if you try to extend the model, let's say the fermionic sector, yes, it's possible. You can make a complicated model. You can have, let's say, different kind of CISO, let's say inverse CISO or linear CISO. Recently, linear CISO became very important because you can have about TeV scale theory. So the corresponding CISO scale is a TeV theory, but again, I don't know how motivated those are because you always require new particles. So it's possible, yeah.
All right, thanks. I think we should stop here. Okay. I would like to thank the audience who spend their time to come to this talk.
And the nice questions, very good questions.
And very nice questions and very entertaining talk, I must say. And yeah, hopefully we can see each other later on. And Saad, if we want to invite you in the future, so be prepared for that.
That would be great.
Yeah, for after a few.
Right.
Yeah. And so let's give applause for Saad for very nice talk. And
thank you.
Yeah. So so we have come to the end of our colloquium. So thanks again for coming. And yeah, have a good night for everybody.
Okay, bye, everyone. Bye, Julio.
You can leave the Zoom if you want.
Thank you.